How do we get from a voltage difference to an electric field? If I know 2 points have a difference of 60 volts, then can I figure out how strong the field in between must be? The answer is yes, and it's easier than you think. This is how we link them together. Here's a conceptual setup. We already know that voltage is the amount of energy you have per charge. An electric field is the amount of force per charge. But the big idea now is that the electric field is the rate at which potential drops with distance. I'll say this again, but slightly differently. The electric field is how fast your potential drops as you move, either further or closer. We'll start with plates because plates work as a good example. We're in a uniform electric field setup. We've seen this before. We know this is positive side, this is the negative side, and it's also on the pre-cheat sheet in the description, but work is equal to charge times electric field times distance, or it's equal to the negative charge times the change in distance. We looked into this why in the last video, but since these are both work, we can equate these two. So QED equals negative Q VB VA. They're equal, right? Because they're both equal to W. What are we trying to do here? I'll show you. If we rearrange this and isolate E, the charges end up cancelling out. We get E equals negative change in V, so VB minus VA, the difference divided by distance. This is the formula we're going to use today, and it's on the free cheat sheet in the description, like I said. And the reason why I derived it really quickly here is so that you don't think that I pulled it out of my bum crack. Formulas don't come out of thin air. What we've done here is we've related electric field to voltage. And what it says is that the field points from high potential to low potential. The bigger the drop in voltage over distance, the stronger the field. So if the voltage drops strongly with how much you move away, that means the field is quite strong too. Here's something super practical. We're going to look at real numbers. If you're standing in a field and this electric field like this, you're standing here. If it drops 120 volts over 0.3 meters, then the electric field is this. It's volts over meters. So 120 divided by 0.3 meters, giving us 400 volts per meters. So time for an example problem, and it's why I drew these electric plates in the first place. Our goal is to calculate the electric field between these two parallel plates, given the voltage and the spacing. Let's say voltage from B to A is 75 voltage, and D is 0.025 meters. That's how far apart the plates are. Since the field is uniform, we can use this formula. V over D, and it's also on the cheat sheet in the description. The math is here. Sub in 75 for V, 0.025 for distance, and you get 3000 volts per meters. The field points from high potential to low potential, so A to B. And if the field is not uniform, so if you've ever seen, those dipoles, not uniform, there's no straight lines, which means we can't use this formula. Instead, we go differential. So E equals negative dV over dx. But on this channel, I never go into any calculus. On this channel, no calculus physics yet. For basic problems, this is enough. In real life, if the field gets too strong, so above 3 million volts per meters, the air literally starts to break down. This is how lightning happens. Electrons accelerate, they smash into the air molecules, and they knock out more electrons in those air molecules, and the air becomes conductive.